Welcome to this problem-solving session. Today, we'll explore a fascinating problem titled Flip Columns for Maximum Number of Equal Rows. We'll break down the problem statement, discuss potential approaches, and evaluate the most efficient solutions. Let's dive right in and tackle this step by step. In this problem, we are working with a binary matrix, which is a grid where each cell contains either a 0 or a 1. The task is to determine the maximum number of rows that can be made completely equal, meaning every value in the row is either all zeros or all ones, after flipping any number of columns. Flipping a column means toggling every value in that column, changing all zeros to ones and all ones to zeros. For instance, if a column contains 0, 1, 0, flipping it would result in 1, 0, 1. The input to our problem is the binary matrix itself, and the output will be an integer representing the maximum number of rows that can be made completely uniform. Now, let's explore some examples to better understand how this works. Consider the first example, where the input matrix is 0, 1, 1, 1. Without flipping any columns, we can immediately see that only the second row, 1, 1, is uniform, all its values are the same. If we tried flipping columns, there's no way to make both rows equal simultaneously in this case. Therefore, the maximum number of rows with all values equal is 1. Now, let's look at another example with a slightly larger matrix. In the second example, the input is 0, 1, 0, 1, 0, 1, 0, 1, 0. Here, if we flip the second column, the matrix transforms into 0, 0, 0, 1, 1, 1, 0, 0, 0. Now, notice that the first and third rows are identical, consisting entirely of zeros. This gives us two rows with all values equal. Hence, the maximum number of uniform rows in this case is 2. Let's examine one more example to solidify the concept. In the third example, the given matrix is 0, 0, 0, 0, 0, 1, 1, 1, 0. Here, no matter which columns are flipped, it is impossible to make more than one row uniform at a time. For instance, flipping any column might make one row entirely zeros or ones, but the others will not align. Therefore, the maximum number of rows with all values equal is just 1. To summarize, the constraints of this problem allow for matrices up to 300 rows and 300 columns, with special cases like single row or single column matrices also being valid inputs. These edge cases, such as when all rows are already equal or when only one row or column exists, should be carefully considered during implementation. To begin solving this problem, one possible approach is the brute force method. This involves systematically exploring every possible subset of columns, flipping them, and checking the resulting matrix to see how many rows become identical. The steps are straightforward. For each subset of flipped columns, you flip the corresponding values, examine if the rows align, and keep track of the maximum count of identical rows achieved. While this method is conceptually simple and guarantees a correct solution, it quickly becomes computationally infeasible. The reason is the sheer number of subsets to evaluate. With n columns, there are 2 n subsets, and for each subset, we need to process all m rows. This leads to a time complexity of O2 to the power of n times m times n, which grows exponentially with the number of columns. Due to this exponential growth, the brute force approach becomes impractical for matrices of even moderate size, so we need a more efficient strategy to handle the problem effectively. Now, to improve efficiency, we turn to an optimized approach that focuses on key observations about the problem. The critical insight here is that flipping columns is essentially a way of making rows equivalent. Specifically, 2 rows are considered equivalent if one can be transformed into the other by flipping a specific subset of columns. For example, if we have a row A equals 1, 0, 1, and a row B equals 0, 1, 0, we can see that flipping certain columns in A results in B, making them equivalent. Instead of explicitly flipping columns, we can calculate a unique pattern for each row that represents its relationship to its flipped counterpart. For instance, the row 1, 0, 1 has a flipped version 0, 1, 0. These patterns can then be stored as strings for tuples for efficient comparison. Using this approach, we count the frequency of each unique pattern with the help of a hash map. The pattern that appears most frequently corresponds to the maximum number of rows that can be made identical. This avoids the need to explicitly flip columns, reducing the complexity dramatically to O, m*n, where m is the number of rows and n is the number of columns. The strategy we ultimately adopt is the optimized, pattern-based approach due to its efficiency and scalability. Instead of evaluating every possible column flipping combination, this method leverages the concept of row equivalence to simplify the process. By converting each row into a pattern, we can focus on counting the most frequent patterns using a hash map, avoiding the exponential complexity of the brute force method. The key realization here is that flipping columns translates into transforming rows into equivalent patterns, and rows with the same pattern can be grouped together. This insight transforms the problem into a much simpler task of counting the occurrences of these patterns. While the brute force approach is conceptually easier to implement, it is computationally prohibitive for larger matrices. On the other hand, the optimized approach is more efficient and well-suited for real-world scenarios, though it requires a deeper understanding of the underlying pattern-based logic. In terms of trade-offs, the optimized method clearly outperforms the brute force approach in practical applications, making it the preferred solution for this problem. Finally, let's analyze the complexity of the optimized approach. The time complexity is O(m*n), where m is the number of rows and n is the number of columns. This efficiency comes from processing each row exactly once to compute its pattern and using a hash map for fast lookups and insertions. The space complexity is O(m), as we need to store the unique row patterns in the hash map. This optimized solution is both time efficient and space efficient, making it a scalable approach suitable for real-world applications. By leveraging the concept of row patterns and avoiding the exponential growth of brute force methods, this strategy allows us to solve the problem effectively without compromising on performance. To solve this problem, we need to determine how to make all rows in a binary matrix identical by flipping specific subsets of columns. A column flip inverts all the values in that column, turning zeros into ones and ones into zeros. The challenge is to find the maximum number of rows that can be made identical after performing these flips. For example, consider the input matrix 1 0 1 0 1 0 1 0 1. By flipping only the second column, the first and third rows become identical, and the output is 2. This illustrates how flipping the right set of columns can align rows, and our task is to maximize this alignment. Now, let's explore some key observations about the problem. Rows are equivalent after flips if their patterns can be transformed into the same row. This means that two rows can be made identical if, for every column, their values are either the same or opposites. For example, row A equals 1 0 1 and row B equals 0 1 0. These rows can be made identical by flipping the second column. The exact column indices we flip don't matter as much as the structure of the row itself. To simplify the problem, we can use a canonical form, which represents the row pattern as if the first element of the row were 0. For instance, 1 0 1 transforms into 0 1 0 as its canonical form. This reduces our task to finding the most common canonical form among the rows. To achieve this efficiently, we use a dictionary, or hash map, to count the frequency of each canonical form. The input matrix is stored as a 2D list, and will generate and store these canonical forms for all rows. We start the algorithm by initializing the necessary data structures. First, we create an empty dictionary, row_counts, to store canonical forms and their frequencies. Then, we process the matrix row by row. For each row, we generate its canonical form. If the first element of the row is 1, we flip the entire row by inverting all values. If the first element is 0, we keep the row as it is. Once the canonical form is determined, we store it as a tuple, which ensures immutability. Finally, we update the frequency count for this canonical form in the row_counts dictionary. For example, in the matrix 1 0 1 0 1 0 1 0 1, the canonical forms are computed for each row, and their frequencies are updated in the hash map. After processing all rows, the canonical forms and their counts might look like this: 0 1 0 appears twice, and its count is 2. This represents rows that can be made identical after flipping. To determine the result, we find the maximum count in the row_counts dictionary, which corresponds to the largest group of rows that can be made identical through flips. This approach eliminates the need to explicitly flip columns, as the canonical form allows us to group rows by their equivalence class under flips. Using a hash map ensures efficient lookup and storage, with the time complexity for counting all rows being proportional to the number of rows in the matrix. The algorithm handles edge cases well, such as when all rows are already identical or when the matrix has only a single row or column. Generating the canonical form for each row takes linear time relative to the number of columns, O(n). Counting the frequencies of these forms in the hash map takes linear time relative to the number of rows, O(m). This gives the algorithm an overall time complexity of O(m*(n), where m is the number of rows and n is the number of columns. The space complexity is also O(m*(n), since we need to store the canonical forms for all rows. For example, in the matrix 1 0 1 0 1 0 1 0 1, the canonical forms are 0 1 0 for all rows. The hash map stores this form with a count of 2. The output, which is the maximum frequency in the hash map, is 2. This represents the largest group of rows that can be aligned through column flips. This Python implementation solves the LeetCode problem number 1072, flip columns for maximum number of equal rows. The goal is to maximize the number of identical rows in a binary matrix by flipping columns. Here's a detailed explanation of the solution. 1. Initialization. We use the counter class from the collections module to keep track of the frequency of row patterns. This helps us efficiently count how many rows can be made identical. 2. Processing each row. We loop through each row of the matrix. For each row, we create 2 patterns. The row itself, represented as a tuple. The complement, flipped version, of the row, where all 0s become 1s and vice versa. 3. Counting patterns. We update the frequency count of the row pattern in the row_pattern_count dictionary. This ensures that we account for both the row and its flipped version. Whichever pattern, original or complement, is consistent across multiple rows will accumulate the highest count. For finding the maximum frequency, after processing all rows, the maximum value in the row_pattern_count dictionary represents the maximum number of rows that can be made identical after flipping columns. This algorithm is efficient and avoids explicitly flipping columns. Instead, it leverages the symmetry between rows and their complements to directly calculate the result. The time complexity is O(m*(n), where m is the number of rows and n is the number of columns, as we traverse the matrix and process each row. The space complexity is also efficient, as the row_pattern_count dictionary grows proportionally to the number of unique row patterns. This concise yet effective approach ensures correctness and handles all edge cases, such as matrices with all identical rows or rows that are completely different. Here, we start by importing the necessary Java utilities and defining our solution class. The method max=rows_after_flips takes a 2D matrix as input and calculates the maximum number of rows that can be made identical by flipping columns. To achieve this, we define a hash map called patternCount to store row patterns and their frequencies. For each row in the matrix, we construct 2 strings, one representing the row's current pattern and another representing its complement, which is obtained by flipping every bit in the row. These 2 patterns allow us to account for both the original row and its flipped version. After constructing the patterns, we increment their frequency in the hash map. This ensures that we are tracking the number of rows that align with each specific pattern or its flipped equivalent. Finally, we iterate through the values in the pattern count map to find the maximum frequency of any pattern. This maximum value represents the highest number of rows that can be aligned by flipping columns. Once this value is determined, we return it as the result. The method is efficient because it leverages the idea of symmetry between a row and its complement, ensuring that we only need to track patterns once and avoid redundant calculations. By using a hash map and focusing on patterns, we achieve a clean and performant solution to the problem. Here, we start with a simple example. The input matrix has 2 rows, 0, 1, and 1, 0. First, we initialize an empty counter called row_pattern_count to keep track of the frequency of row patterns and their complements. Now, for the first row, 0, 1, we treat it as a pattern by converting it into a tuple, 0, 1. Then, we calculate its complement by flipping each bit, resulting in 1, 0. We update the counter by incrementing the frequency of the pattern, 0, 1, to 1. Next, for the second row, 1, 0, we again convert it to a tuple, which gives the pattern 1, 0. Its complement, when all bits are flipped, is 0, 1. Instead of incrementing 1, 0 directly, we update the frequency of its complement, 0, 1, in the counter, raising its frequency to 2. After processing all rows, the final state of the row_pattern_count is 0, 1, 2, 1, 0, 0. This indicates that the pattern 0, 1 appears twice when considering both rows and their complements, while 1, 0 contributes nothing directly. The maximum frequency in the counter is 2, which means we can make all rows identical by flipping columns appropriately. Thus, the output for this example is 2. Now, let's analyze another case where all the rows are already equal in the input matrix. The matrix here has 3 rows, all of which are 1, 1, 0. In this case, we again start by initializing an empty counter, row_pattern_count. Since all rows are identical, we process each row in the same way. For the first row, 1, 1, 0, we convert it to the tuple 1, 1, 0 as the pattern, and its complement is calculated as 0, 0, 1 by flipping each bit. We update the counter, incrementing the pattern 1, 1, 0 by 1. The same process is repeated for the second and third rows, incrementing the frequency of 1, 1, 0 to 2 and then 3. The complement 0, 0, 1 remains unused in this case, as it doesn't match any row. The final state of the counter is 1, 1, 0, 3, 0, 0, 1, 0. Now, let's examine a more diverse case, where the input matrix contains mixed patterns. The rows are 0, 0, 1, 1, 1, 0, and 0, 0, 1. After initializing the counter, we process the first row, 0, 0, 1. Its pattern is 0, 0, 1, and the complement is 1, 1, 0. We update the counter by incrementing the frequency of 0, 0, 1 to 1. For the second row, 1, 1, 0, the pattern is 1, 1, 0, and the complement is 0, 0, 1. This time, we update the frequency of the complement 0, 0, 1 in the counter, increasing it to 2. Finally, for the third row, 0, 0, 1, the pattern is again 0, 0, 1, and the complement is 1, 1, 0. We increment the frequency of 0, 0, 1 to 3. The final state of the counter is 0, 0, 1, 3, 1, 1, 0, 0. From the counter's final state, we see that the pattern 0, 0, 1 has the highest frequency of 3, while the complement 1, 1, 0 doesn't contribute directly. This frequency of 3 represents the maximum number of rows that can be made identical by flipping columns. Thus, the output for this example is 3. With this approach, we can handle different row patterns efficiently by leveraging the relationship between rows and their complements to find the maximum count of identical rows. The time complexity of this solution can be analyzed by breaking it down into distinct steps. First, we iterate through each row of the matrix. If the matrix has m rows and n columns, this iteration contributes O, m. Next, for each row, we generate both its pattern and its complement. Converting a single row into a tuple takes O, n, and generating its complement using a list comprehension also takes O, n, so processing one row requires O, n, plus O, n, which simplifies to O, n. When this is done for all m rows, the total contribution becomes O, m asterisk n. Additionally, each row's pattern is added or updated in a counter dictionary. Since dictionary updates have an average complexity of O, 1, and we perform this operation for each row, the total cost for this step is O, m. Finally, finding the maximum frequency among the dictionary's keys involves checking up to m keys, which takes O, m. These steps together give us the overall time complexity, which we will summarize next. Combining all the steps we discussed, the dominant term driving the time complexity is O, m asterisk n, which comes from processing the rows. The additional costs of dictionary updates and finding the maximum frequency, both O, m, are much smaller in comparison. Therefore, the overall time complexity of the solution is O, m asterisk n. Now, for space complexity, the largest contributor is the counter dictionary, which stores row patterns for their complements as keys. In the worst case, where all rows are unique, the dictionary can store up to m keys, each of length n. This results in a space requirement of O, m asterisk n. Additionally, we temporarily generate two tuples for each row during processing, the row pattern and its complement. These require O(n) space each, but since they are discarded after processing each row, the total temporary space at any moment is O(n). Combining these, the space complexity is dominated by the counter dictionary, giving us a total of O(m*(n). Let's now compare the optimized solution to a brute force approach. A naive method would involve trying all possible subsets of columns to flip and checking how many rows become identical for each combination. Since there are n columns, this results in 2 to the power of n possible combinations. For each combination, we would process all m rows, and comparing rows involves O(n) time. This means the brute force method has a time complexity of O(2 to the power of n times m times n, which grows exponentially with the number of columns, making it infeasible for larger inputs. The optimized approach avoids explicit column flips by encoding rows as patterns and their complements, counting these patterns, and finding the maximum frequency. This requires only a single pass through the matrix to compute the patterns, with a time complexity of O(m*(n). By avoiding the exponential growth of the brute force method, the optimized approach is significantly faster and practical for larger matrices. Now let's analyze the best, worst, and average cases for this algorithm. In the best case, all rows are identical, leading to just one unique pattern. Even in this scenario, the algorithm still processes all rows, resulting in a time complexity of O(m*(n). In the worst case, all rows are distinct, which means the counter dictionary will have n unique keys. Despite this, the time complexity remains O(m*(n), as the dominant operation is processing the rows. For the average case, we assume a mix of identical and distinct rows. The algorithm still processes each row, so the time complexity again remains O(m*(n). To formally prove this, we can sum the complexities of key operations. Iterating through rows takes O(m), generating row patterns and their complements takes O(m*(n), dictionary operations require O(m), and finding the maximum frequency adds another O(m). The dominant term here is O(m*(n), confirming that the overall time complexity is O(m*(n). Similarly, the space complexity remains O(m*(n), dominated by the counter dictionary. One of the most common mistakes when solving this problem is ignoring edge cases. For example, what happens if the input matrix is empty, has only one row, or consists of just a single column? Many algorithms fail in these scenarios, often leading to runtime errors. To avoid this, it's essential to account for these situations explicitly and handle them separately if needed. Another mistake is failing to optimize the flipping strategy. Randomly flipping columns without a clear plan can result in unnecessary computations and inefficiency. Instead, focus on patterns in the matrix, such as dominant rows or columns, to guide your flipping decisions strategically. Finally, overcomplicating the solution is a frequent issue. Candidates sometimes attempt overly complex recursive or backtracking approaches, which are harder to debug and often exceed time limits. Simplifying the problem by leveraging properties like symmetry, row equivalence, or greedy strategies can make your solution both cleaner and more efficient. Another critical mistake to avoid is incorrectly handling row patterns or parity. Misunderstanding how flipping a column affects the equivalence of rows can lead to incorrect results, especially when toggling binary values. To address this, it's important to clearly define how each column flip impacts the state of the rows and ensure all calculations are applied consistently. Inefficient subset generation is also a challenge. Generating all possible column subsets without filtering out unlikely candidates can result in exponential time complexity, which is impractical for larger inputs. A better approach is to use bitwise operations or pruning techniques to narrow down the solution space and focus only on promising subsets. When tackling this type of problem in interviews, pattern recognition is key. Think of each row as a unique state or signature that can change when columns are flipped. The goal is to maximize the number of identical states across all rows. It's also important to understand the trade-offs between different approaches. While a brute force method is straightforward to implement, it's often inefficient for larger inputs. Greedy or hash-based techniques can provide a better balance between simplicity and performance. Additionally, always be aware of the time complexity of your solution. For instance, a brute force approach might have a complexity of 2 to the power of m asterisk n, where m is the number of columns and n is the number of rows. Optimized solutions significantly reduce this complexity. During an interview, communicate your thought process clearly. If you get stuck, explain what you're trying to achieve, such as maximizing identical rows with minimal column flips, and involve the interviewer in discussing potential strategies. Finally, exploring related problems, like matching subsets or graph traversal challenges, can help you build a stronger foundation for solving matrix-related problems. There are several alternative approaches to solving this problem. A hashing-based approach involves representing each row as a binary string or tuple and hashing their states before and after column flips. This allows you to count the maximum number of identical rows efficiently. While this method is faster than brute force, it does require additional space for the hash table. Another option is a greedy strategy, where you focus on flipping columns that maximize the alignment of the most frequent rows or states. Although this approach is efficient for most practical inputs, it may not always yield the optimal solution. Lastly, recursive backtracking with memoization allows you to explore different column flipping combinations while storing already seen states to avoid redundant calculations. This can be effective for smaller matrices, but without proper pruning mechanisms, it can lead to exponential growth in runtime. Each of these methods has its trade-offs, so choose the one that best fits the problem constraints and input size. Great job! In this session, we tackled the problem of flipping columns to maximize the number of equal rows. We reviewed the brute force approach and discussed how optimization can improve performance. Remember to apply these concepts in similar problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!